Let's get started. Today we'll talk about recursion a little bit more, and we'll do the test review for your test on Tuesday. Currently, right now, I believe homework 6 is due Saturday night, maybe Sunday night. If you need an extension, request it as usual using the WebAssign. So what we need to do is talk about recursion just a little bit more. You have a few problems on homework 6 that you need to prove by induction. I'm going to work one of them. So we'll do that, and then we'll get into recursion. So one of the parts of problem 1 you have to do So here's the problem. We want to prove this is true by induction. So what is this on the right-hand side? What do we call it? We don't call it polka dots. You have no ideas. Closed form. We call it closed form because I don't have to have any dots in it. What's on the left-hand side? Yeah, it would be nice if it was called open form. But this is a summation. And it's always also called a series. So a lot of times we want to prove that these two things are equal, so I can use a closed form or a formula instead of doing a series. Why would I want to use this instead of that? It's shorter, a lot less calculations. Also, how many calculations are over here? N of them. How many calculations are over here? 1. So, can you think of a time where I might want to do this one instead of that one? No? When n is small? Maybe? And I might have to do it by hand, maybe? So you might want to do this one if I have to calculate all these numbers anyway. Right? Because I actually could write this recursively. Because the sum on the left-hand side, let's say that this was called f of n. And I could write this as a recursion as f of n minus 1 plus what? Well, if you can't answer that question immediately, you should figure out what f of n minus 1 is. So I want you to write that on your paper. What is f of n minus 1? What goes in the blank? N minus 1 times n minus 1 factorial. That should not be hard. That is one of the reasons why you take this class, is to practice doing things like that, is to recognize if I change an input, how does that change what I'm actually calculating. So now that you know what this is, what's the difference between these two? So if you don't know what this is, I can subtract them. So what do I get if I subtract the left-hand side of f of n and f of n minus 1? So over here, I just get f of n minus f of n minus 1, right? What do I get on the right-hand side? I just get n times n factorial, right? Because all these other terms line up. Everything else here is in f of n. Yes? All the terms in f of n minus 1 are actually in f of n. So the only difference is this last term on f of n, so I can just write this. So there was a question on the piazza about what is the cheat method for finding a recurrence. So here is a function, and the cheat method for finding a recurrence is by writing a definition of that function for an earlier number and then subtracting them. So the definition of a recurrence is something that uses a smaller value as an input for the function, so the function actually refers to an earlier value. So that's the definition of a recursion. So you have to have something that looks like this. Doesn't matter what that is, and then some other stuff. So a recurrence looks like that, and it has to have one other thing. And what is that? It has to have a basis, right? Because I can't look back forever. I have to start somewhere. So in order to make a basis for this, what would make sense to start at? Should I start at f of 0? No, because I don't have any zeros in my formula. It would make more sense to start at 1, right? So I write down what f of 1 is, and it's equal to 1 times 1 factorial, which is equal to 1, right? So now we have a recursive definition for this. And we have a closed form also. So there's a few different things here that we could prove are equal. I did just want to show you the cheat method. So that's what that is. So the cheat method is if I need to come up with a recurrence for something, so if I have f of n equals something, I figure out what f of n minus 1 is. And that's not hard to do because all I have to do is copy everything, and everywhere I see an n, what do? I replace it with n minus 1 and put parentheses around it so I make sure I don't make any errors. And then I just need to subtract one from the other. And then whatever I get over here is, let's say that's a and this is b. I get a minus b. And then I just solve for f of n by adding f of n minus 1 to both sides. And then I figure out what the basis is. So whatever it happens to be, I just write that down, and now I have a recursive form. So if I've ever given you a formula that's a closed form and I ask for a recursive form, that's all you need to do. Now, on the example we looked at the beginning, anything that is a nice sum like that is really easy to write in a recursive form. Because there's n terms, and so the nth one is very easily written in terms of the n minus 1 one because it just has one more term added on to the n. So that should be easy. That process is something that we do both for making a recurrence and for making a summation, figuring out what formula goes in the middle of the summation. So that's what I want to do next, is figure out how do I write the summation for this. Can I do what? Show the bottom? Yeah. So I'll do a couple of examples of this in a minute. So we're going to do a summation for this and a proof, and then we'll go back to the cheat method. So right now, while people are writing this down, if you already have it written down, go ahead and figure out how you write the summation for the left-hand side of f of n here. Okay, so the process I go through is I write down the summation, and then I try to figure out what the last term is, and I write it instead of with n, I write it with k's. I like to use k's instead of i's because i's look like 1's, which also look like l's. So that's why I use k's. So that's what I recommend to you so you don't get mixed up about which thing is which and make a mistake. Okay, and then I have to have a k equals something on here. Yes? This is k times k factorial. So k factorial is a function, and it gets multiplied by k. So if the factorial was applied to k times k, there'd be parentheses around k times k. Thank you for the question. Okay, so now I need to figure out where k starts. What's the smallest term in the summation? 1, so k should be 1. And then the largest is n. So that looks pretty good. And then I can copy over the right-hand side. All right, so let's prove this by induction. So I'm going to write the left-hand side. Now, you might be tempted to write 1 times 1 factorial inside that summation, but you shouldn't, because all I can do is replace the n's with 1's. So this is 1 times 1 factorial. 1 factorial is just 1, so that's 1. And this is 2 factorial minus 1. 2 factorial is equal to what? 2, because it's 2 times 1. So we get 2 minus 1, which is equal to 1, and that is equal. Then I write assume, and I copy over what I'm trying to prove. And then I write the prove, which is exactly the same, but everywhere I have an n, I replace it with n plus 1. Notice that I don't change what's inside this summation because there's no n's in there. So there's my problem set up. And then we start with the left-hand side of the prove. And set it equal to the left-hand side of the assume. And then I have to fix it. And we just figured out that the difference between these two was just the last term, which is n times n factorial. And then I can replace the left-hand side of the assume with the right-hand side of the assume. So you still leave this here. So the right-hand side of the assume says that that's n plus 1 factorial minus 1. So that's the right-hand side of the assume. So I'm just doing a substitution. And add n times n factorial. Because that's what's over here. Yes? Yes, thank you for fixing that. Sorry about that. I'm going to write that over again. By the way, you can do an assume with n minus 1 and prove for n, so that is fine. You can choose whichever one you want to do. Okay, so I replaced that with n plus 1 factorial minus 1, and then just copy down the rest. All right, now what we need to do is get it to look like n plus 2 factorial minus 1. So I've got the minus 1, right? I just need to combine the other stuff so it can make it into an n plus 2 factorial. So the first thing I need to do is just get them together. So I'm going to put the minus 1 on the right-hand side. Does anybody have an idea of what to do next? Factor out an n plus 1 factorial because it's in both of the terms. And what I get after I factor it out here is a 1. So I get 1 plus the quantity n plus 1. And then I still have the minus 1. So I factored out an n plus 1 factorial out of the first two terms. And inside the parentheses, we have what? N plus 2. And so is there any magic you can do to finish this problem? That is the definition of n plus 2 factorial, right? This right here is the definition of n plus 2 factorial. Raise your hand if you see that. Raise your hand if you don't see that still. Okay, so n plus 2 factorial is the product of all the numbers from 1 up to n plus 2. N plus 1 factorial is the product of all the numbers from 1 up to n plus 1. So the only difference between those is to take n plus 1 factorial and multiply it by the missing term, which is n plus 2. And if that doesn't make sense, you should write it out on your paper. So now we're done because we have the right-hand side looking like what we wanted to prove. And all of these are fully reversible things that we've been doing, so everything on each line is equal to the last line. Any questions on this problem? Yes? No, I don't. No. You don't need to copy down the left-hand side of the proof if you've already got it on the paper. So, you know, when I start doing my equals, as long as I've got it there, it's fine. Yes?
When you started out doing this problem,
yes.
you were doing recursion stuff?
Yeah.
And then you switched over to doing an induction proof. Are those usually going to be tied together? Or?
No, I was just pointing out that we could write a recursion for it because that's something else I wanted to do today. So we're going to go back to that now. So this is a separate problem. I'm sorry that was confusing. So separately, we figured out how to write a recurrence for the left-hand side of this, and then we did an induction proof that the left-hand side is equal to a closed form. Thank you for asking that question. Okay, so going back to the cheat method for finding a recursion. So one thing I mentioned before is that I might actually want to use a recursion to calculate something if I already have to calculate all the values. So if I already have to calculate all the values, I could put them in a table and then use the recursion to do a nice table lookup and have less complicated math to do. So if I had to do all the values of that summation we were looking at, I might as well save them in a table and add those. And let's see. What if I have f of n equals a to the n, and I've asked for a recursion for that? So the cheat method is to write over this formula again, but put n minus 1 in there. Subtract the left-hand sides. Subtract the right-hand sides. And then solve for f of n on the left. By the way, all of that's in the exponent. And I need also a what? A basis. So if I ask you to give me a recurrence and I've given you a function, you can do just exactly that. And did you notice that I actually haven't tried to make this simpler at all? Because I didn't ask you for the simplest, most coolest looking one. I just asked you to write a recursion. And a recursion has f on one side and f on the other side where the number is smaller, and it has a basis. That's all you have to do. So the cheat, I call that the cheat method because you could use robot brain for that. I should call it robot brain method. So that's nice because now if I need a recursion, I can make one easily. Can you make this look nicer? How do you do it? Factoring is your friend. So if I had to make that look nicer, so usually if I have to write a recurrence for something, it's because actually what I'm trying to do is do less complicated math. Because I have to calculate all the values, so I could use a previous value to do simpler math. When might you want to do that? When you have unimaginable systems to you that actually, you want to minimize the computation time. Can you think of any systems where I might want to minimize computation time? All of them? Okay, that's not a very restrictive answer. What kind of systems do I want to minimize the computation time? How many of you play video games? Okay. How many of you play video games that are 3D? Okay. If you play 3D video games, they are doing a heck of a lot of stuff while you're in there. How many of you play video games that have a whole bunch of characters in them? Okay, so every one of those characters has a whole bunch of calculations going on to figure out what they're going to do next. If I have to do a whole bunch of calculations for like 100,000 characters in my game, I better do them as fast as possible. And if I can, I'd like to have them in a table so I can look them up. And the table better fit in my memory too. And if I'm on a console, it used to be consoles were like really limited. Now you can really think of like a PSP or something. You're going to have limited memory. So when you're building a game system, you really have to balance your computation and your memory usage to optimize it, because basically everything that gets done in your game has to be done between the frames that you're looking at. How many frames per second are in a game? Okay, variable is a general answer again. What is a minimal number that you have to have? 30. Why is it 30? Because if it's not 30, you can detect that they're frames. So it's usually 30 to 60, and they don't usually bother with more than that because that's extra work we don't need to do. So your human brain, if you have 30 frames a second, it's like those flip books with cartoons. Your human brain will integrate them and assume that there's actually people moving and stuff. So games have to balance like how many of those are going to put on the screen. And in between doing those, they've got to do any calculations to figure out all the math that's going on in the world. So you might actually want to have some additions to do instead of some multiplications, because they actually technically do take a lot less time. Okay, so I might want to make this so it's actually I don't have to calculate so much stuff. Yes?
So I noticed that the resulting recursion formula is the formula minus the formula for n minus 1.
That's exactly what it is.
You just do that straight?
Sure. Okay, but we haven't gotten the benefit of making a simpler calculation yet. That's what I'm talking about. So we can make a simpler calculation by figuring out what the heck is this. A to the n minus a to the n minus 1. I can factor an a to the n minus 1 out of it, and I get a minus 1. So that's one less exponent that I have to calculate. And if I happen to have a table of a to the n minus 1, that's already been calculated, I could use that. So this wasn't a great example for saving some calculation by doing this. So that's because the cheat method does not give me the most efficient way to get the new thing from the old thing. So now I should look at this formula and say, is there a better way to get from f of n minus 1 to f of n besides subtracting both sides? How can I calculate this one based on that one? Multiply it by a. So a better way is actually f of n is equal to f of n minus 1 times a. Now I've saved some calculations because I'm not doing any exponents, right? Because I'm just using a stored prior value and multiplying it by a, which is a lot less computation. You can't get that with the cheat method. You have to use real brain for that. Yes? You are allowed to do the cheat method, which is why I spend time going over it. Okay, so that was just an introduction of why we might want to have recurrences. The cheat method will not give you the one that gets you some benefit, but it will answer your questions on the tests that say find a recurrence given this formula. And on the homework, too. But you should actually spend some time trying to figure these out. Don't spend forever, but a few minutes per problem, and then if you get it, it'll be sort of like winning a little video game. It's kind of fun. Okay, so you have some problems like that on your homework. So some of your problems look like this, where you are given formulas like this. What's the difference between something like f of n and a sub n? Is there a difference? I want you to write down, what's the difference between something like f of n and a sub n? Is there a difference, and what is it? So what does a sub n mean? Write it down. But a basically equivalent question is, when would I use a sub n and when would I use f of n? Raise your hand if you have an answer that you agree on with your neighbor. Anybody know? Raise your hand if you think there is a difference between something like a sub n and f of n. Raise your hand. It's fine. Raise your hand if you think there's a difference. Okay? And raise your hand if you don't think there's a difference. So many of you aren't voting. Raise your hand if you don't know. Okay. Good. Thank you for voting. There isn't a difference. There is no difference. So they are just different ways of writing the same thing. However, they are usually used in different contexts. So remember that part of what we're doing in this class is learning some different languages. This is mathematician language. Mathematicians also use functions, but if they're going to actually use a whole bunch of these at the same time, they like to use subscripts because you get to write less things than putting parentheses all the time. That's literally the difference, is that they're using a subscript instead of parentheses and putting that same number in there. The reason why they're doing that is because they're going to do things like this. And that's a heck of a lot more of a pain than writing this. That's the main difference. The other difference is I'm usually going to use f of n if I'm going to calculate it once and I'm not going to put a bunch of them together. So that's really the only difference. There's not a difference. The reason why I ask you is because sometimes people look at it and they're like, I don't know what a sub n is. It just means there's a parameter. Yes? That is true. So that is a great answer of why they're different. So if you're talking about all of those subscripts are natural numbers or integers like we usually are in this class, there is no difference, but in calculus there would be. So I could not write this for real numbers that aren't whole numbers. So that's a great point. So that's the other thing. If my function is continuous, I have to use a function and not a series or sequence. Okay, so these are the kind of problems where you have to write a recurrence. Again, you can use the cheat method on those. It's totally fine. This problem is not as hard as it looks. Give a recursive definition of Pm of n, the product of the integer m and the non-negative integer n. There's nothing special about non-negative. What does it mean? It just means it's 0 or bigger, right? So how do you translate this into math? Delete that. It's an integer. Who cares? Everything we do is integers. Okay? Oh, it's recursive, so I can just go ahead and write this, and I got to have something like this, and then something, right? It's got to be recursive. So the thing I have to do to figure out what this is, I can't use the cheat method until I know what the original formula is. So what is the product of m and n? How do you write that? M times n. So hard. I don't know why, but every single semester, every single student's like, what? Okay, it's not that hard. This is Pm of n is equal to that. So if you're having problems on WebAssign, hopefully you got this, but you wrote mn, and you need to put the times in there, that's all. So now you can use the cheat method to get that. Yes? No, you can write them next to each other. It just happens to be that on WebAssign we have a times in that. Okay, so we're going to derive the closed form for a recursive sequence. What's the difference between S of n and F of n? Nothing. It's just different letters. There's no difference. So we're going to do an example problem. We're going to do example 4.1 from your packet. S of 0 is equal to 2. S of 1 is equal to 5. S of n is equal to 5 times S of n minus 1 minus 6 times S of n minus 2. And I want to find the closed form. That's an S, that's a 5, sorry. So this recurrence, oh, that's what you were wondering what the heck that was, sorry. Finding closed forms is a pain. However, there's a nice method on packet 4, page 2. So the method is really related to something you might have done when you were trying to figure out derivatives for particular formulas, is that you guess and then you fix it. That's exactly what we're going to do. So we're going to guess, and the reason why we're going to guess is we just had this formula that f of n equals a to the n, and the recursive formula was equal to f of n minus 1 times a. So what this has in common with this is that the current value is a number times some previous value, minus another number times another previous value. But something raised to a power has this formula that looks like one of these terms. So we're going to guess that s is some kind of power function. That's what we're going to guess. And we're going to guess that it's some constant a times some root raised to the n. So if this is true, I want you to write down what s of n minus 1 is. And also write down what s of n minus 2 is. So just use the formula, and everywhere you see an n, put an n minus 1. And if that was true, then I could plug that back in to my S recursive formula, so I can actually put just these two on the right-hand side. So I just put these in to the right-hand side here and get S of n equals 5 times AXN minus 1. So all I'm doing is substituting in the right-hand side of S of n minus 1 for S of n minus 1 in this formula. And then I'm going to do the same thing for S of n minus 2. Are there any s's on the right-hand side? No. So, yay, we're on our way to a closed form. We don't know what a and x are, but we're going to figure it out. So, in order to figure out two variables, I need to have two equations, right? Well, the cool thing is I have two prior values of s. I know that s of 0 is 2 and s of 1 is 5. So I can use that. Actually, the other thing I'm going to do is I skipped over a part. Sorry. I need to write also this formula over here. Sorry about that. Okay, so I need to also plug in my left-hand side. And then I'm going to divide out as much as I possibly can. So I can solve for x or a or something, hopefully. So a, I could just completely cross out of all the terms, right? So x to the n is 5x to the n minus 1 minus 6x to the n minus 2. All I'm doing right now, by the way, is trying to figure out what x is. And then later I'll go back and try to figure out what a is. What, does anybody have an idea of what we might want to do next? Yes? Divide everything by x to the n minus 2. So I'm going to get x squared equals 5x minus 6. Thank you. Okay, and if I set this equal to 0, I can actually solve this with the quadratic equation, right? So I can get x equals minus b, which is minus 5. I divide it out by x to the n minus 2. So x to the n divided by x to the n minus 2, I subtract the powers. So n minus n minus 2 is just 2 on the left-hand side. And on this side, x to the n minus 1 divided by x to the n minus 2 is just x. And x to the n minus 2 divided by x to the n minus 2 is just 1. Thank you. And then, so the quadratic formula is if I have a x squared plus bx plus c equals 0. My quadratic formula is x is minus b plus or minus the square root of b squared minus 4ac all over 2a. It factors, but you need this in case it doesn't factor. But let's just do the factors. How does it factor? So that means my two solutions is x equals 2 and x equals 3, right? Thank you for telling me it factors. As I told you, brain cells don't work up here. I just have to use robot brain. It's okay. Okay, so does this match with our original assumption? If x has two values, this isn't quite right? Because this only has one value for x. So I need to fix my guess. But it's really close. So all I need to do now to fix it is make it the sum of two of these. So since I know that x equals 2 and x equals 3 are roots, by the way, this thing we derived right here, this is called our characteristic equation. And by the way, all of this is in the packet. And you can review it. So we know we have two roots, so we're going to fix our guess. So S of n must be equal to, let's call that x1 and x2, some constant times x1 raised to the n plus another constant times x2 raised to the n. By the way, you don't need to be able to derive this. You should memorize this. This is probably the only thing in class I'll ask you to memorize, is how to get the characteristic equation. But I'm only ever going to give you things with two forms, so you're always going to have x squared minus something minus something. So it's always going to be a square, because I don't want you to have to solve cubic stuff on the test. All right, so now we know what x1 and x2 are. We already figured those out. So I can write that down. And now I have two unknowns, and I need two equations for two unknowns. So I'm going to use S of 0 equals 2 and set that to C1 times 2 to the 0 plus C2 times 3 to the 0. And S of 1 equals 5. It's going to be C1 times 2 to the 1 plus C2 times 3 to the 1. And then I'm actually going to figure out what those are. So I need to get rid of the 2 to the 0s and stuff because they're distracting. So that's 2C1 plus, sorry, not 2C1, just C1 plus C2. Because 2 to the 0 is 1 and 3 to the 0 is 1. And 5 is going to be equal to 2C1 plus 3C2. And I can solve this of several different ways. I can solve the first one for C1 and then plug that into the second one. So now I have C2 equals 1, and so C1 must be 1. So now that I know those, I can go back to my formula, which is up here, and just write S of n equals 2 to the n plus 3 to the n. And since I have a closed form, I don't actually need any basis because this will actually give me the basis. I actually just use the basis to get this, right? So these were using the basis to figure out what those constants were in the closed form. So this is basically a process for solving what's called a linear homogeneous recursion. So linear homogeneous, so linear means line, right? So that means I'm not actually like multiplying two recurrences by each other. I'm just going to add them. So I'm going to add two functions. And homogeneous means all the terms look the same. Yes? Yes, this is our closed form because there's no s's on the right. We had closed form before, like when I had C1 x1 to the n plus C2 x2 to the n, but I didn't know what C1 and C2 were. So I'm not done until I actually figure out what all the variables are. Okay, so let's do one more. Here's a really easy one. So all I want to do is figure out what the closed form of this is. Can anybody guess what the root is going to be? It's going to be 3. Because every time I do something, I'm multiplying the previous one by 3. So it's going to be a power of 3 multiplied by a constant. You don't have to be able to do that. You just have to use robot brain. So robot brain says, replace s of n with ax to the n. Replace s of n minus 1 with ax to the n minus 1. The a's cancel out. And I can also divide by x to the n minus 1 on both sides. And I get x on the left and 3 on the right. So s of n is a constant times 3 raised to the n. And in order to figure out what that constant is, I have to use my basis, which is 0. So s of 0 is equal to 2, which is equal to c1 times 3 raised to the 0. So c1 is equal to 2 because that's just a 1. Yes.
So these you just always assume that it's going to be in that form?
Yes. There's one other thing you need to learn so you can do them. Which is that occasionally we will get a double root that's repeated. So I'm going to see if I have a problem here. If I don't, I'll just make one real quick. Yes, I can put it back up. There we go. I got one here. Okay, is everybody ready to move to the next one? So by the way, I'm doing problems that are already worked in the packet so you can look them over again. So we're going to do example 4.4. S of 0 equals 2. S of 1 equals 9. S of n equals 6. S of n minus 1 minus 9. S of n minus 2. And you can skip over the ax to the n stuff because if I have two terms, I know that s of n is going to be x squared. S of n minus 1 is going to be x, and s of n minus 2 is going to be 1. So I showed you the derivation, which means that actually, if you have a whole bunch more terms, you'll have a polynomial that's the characteristic equation that would have higher powers. I set it equal to 0 by moving everything to one side. And then I can probably factor this with 3's. Now the trouble with this is my formula that I memorize, which is once I have two roots, I multiply the first one by a constant and I multiply the second one by a constant. However, any constants that these are, they could be added, and this would just be 1 constant times 3 to the n. So I need to separate them. So I wouldn't get a double root unless there was something weird going on, and what that is that this is multiplied by n. So if you have a double root, you multiply the second term by n. It's exactly like partial fractions and derivatives. Yes. You have heard it before. Yes.
So when you say a double root, you mean that it's a function squared where you get your root?
Well, it's a double root because it's repeated. So 3 is a root of x minus 3, and it's a root of x minus 3. So I have 2 roots for this equation. So the roots are where the equation equals 0. So if the equation equals 0 twice at that place, it's a double root. So if I had x minus 3 times x minus 3 times x minus 3, that'd be a triple root. So this is a double root. So however many terms, if there was a third term, I'd have to multiply and it was a 3, I'd have to multiply the third one by n squared.
So if you always, whenever you have two of the same root, you just pick one of them and throw it out. If you had 3 of the same root, would you pick 2?
If you have 3 of the same root, so if my characteristic equation was like this, and this totally can happen, I just won't give you a problem like this, you would get C1 3 to the n plus C2 n 3 to the n plus C2 n squared 3 to the n. That's what you would do. Well, I'm not going to give you any problems like that. So if that didn't make any sense to you, you can delete that from your brain. Yes? This is exactly like differential equations. Yes? Yes? Yes, it should. So this is an aside. So if that didn't make sense, just don't write it down. Okay, now we have to figure out what C1 and C2 are. We use our basis for that. So we have S of 0 equals 2, S of 1 equals 9. And then I write down my formula, C1, but I plug in a 0 for n. Notice that I'm not skipping any step. I'm not skipping anything. I'm writing down everything. I totally recommend that you do that. Because a lot of the times if you're like, oh, that's a 0, so I don't have to write anything down, you're going to mess it up. So just write it down. And then multiply it out and say, oh, that whole term is 0. And this is actually just a 1. So we have C1 equals 2. And then I can plug it in. So we get 9 equals 2 times 3 plus C2 times 3. Okay, so 9 equals 6 plus 3C2. 3 equals 3C2, so C2 equals 1. So now I plug that back into my formula. And that's my final closed form. I only need a basis when I have a recurrence. When I have a closed form, I don't need a basis. So I have, I'm going to spend the rest of the time working some problems from your exams. And we do want to hold review sessions for you, but none of your TAs is available on Monday night. However, I will post on Piazza and ask if any of your peer tutors are available, and we'll reserve a room so you guys can study together on Monday night, and your TAs will help the other class on Tuesday night. So our exam is on Tuesday. You are also welcome to go to Bitzer's class on Monday, where he will continue to review for. Also tomorrow, he's doing some test review. It's in this room, 9:35 to 10:25, and on Monday he'll do a review because his test is on Wednesday. Yes, probably the TAs are available tomorrow night. Anybody want to study tomorrow night? Yeah, 2 people want to study tomorrow. You can just send them a note and ask them to help you. I figured that most people would want to wait till next week. Because I would. So I apologize, I'm not too exciting today. I really don't feel very well, but so not too energetic. Okay, so the first part of your test, super easy, set theory stuff. I'm not going to work it because we don't have a huge amount of time. But here's your practice test. You've got some sets, you need to find the intersection. So A intersect B. I just look if anything overlaps. It's the empty set. You may also write it like this. So either one of those answers is fine. When I have two bars, that means how many things are in this set. So I take the union of A union C. 1, 2, 3, 4, 5. There's 5 things that don't overlap within those two sets. A minus C is everything that is in A that isn't in C. So I have the empty set in A, and I have A in A that is not in C. So that is the set containing all the elements that are in A but not in C. The power set of B is all the subsets there. So I need to have the empty set first, the singleton sets, all the doubleton sets, and the triple. So your answer is a set, by the way. So you need to have those curly braces in order to get the right answer there. And the last question says, if the power set of S has 64 elements, how many elements does S have? So the size of the power set of S is equal to the n, where the size of S is n. So 64 equals to the n. I need to figure out what n is. What is that number? It is 6. So the size of, oh, that was just wrong. Size of S is 6. You should post your pictures to Piazza. Okay, so you need to do a set theory and predicate calculus proof. So you need to first translate all these into predicate calculus. So when we have a subset, remember that that was the implication operator. So when I say P is a subset of Q, that means for every element of P, if X is an element of P, then it is an element of Q. So line 1 is for all X, X is in P, implies X is in Q. You could also define that X is in P equals P of X. And in fact, even if you don't write that, I'll assume that's what you mean if you write P of X. So probably what I would do is write it like that. The second one says for all X, Q of X implies S of X and T of X. Remember that an intersection is a little and underneath. The third one is for all X, S of X implies R of X or T of X. So not T of X because it's in the complement. And the last one is there exists an X1 so that X1 is in P. So those are all given. And you will get some points for doing the conversion of the set theory into the predicate calculus. Yes? Yes, we do. 2 and 3, we should put some parentheses. Thank you. That was a good question. Now, when you're doing a set theory proof, you should not combine there exists with for alls until absolutely necessary. The reason is, as we've seen in our truth table proofs before, that we can't combine there exists unless we absolutely know that the same thing is the thing we're talking about. Remember that we said that if there exists a blonde person and if there exists a blue-eyed person, that does not mean that there's a blue-eyed blonde person. So if I get 2 there exists, I'm not absolutely sure that I can combine them together. So remember that every line in a proof is anded together. So I can combine all these for alls all day and still keep for alls. But as soon as I introduce anything with that there exists, I'm not going to be able to just do anything I want. I have to think about whether I can combine things. So what you should do is figure out, how can I figure out that I want to prove actually there exists X1 so that R is in, X1 is in R. Okay, so it looks like I could do hypothetical syllogism with lines 1 and 2. And I did put parentheses around there. And we've got an S and a T on line 3. I can't use hypothetical syllogism because the left-hand side doesn't match the right-hand side. So what I could do is switch the the implication inside line 3 into an OR. And then rearrange to get the S and T together. And this is just commutative. And then I want to switch it back into an implication so I can do hypothetical syllogism, but I'm going to first use De Morgan's to put these together to get S of x and T of x with what outside? A naught. And once I have that, that looks like suspiciously like an implication. And once I have S of x and T of x, I can get for all x, Q of x implies R of x because that S of x and T of x overlaps. And then, did I have anything else? Oh, I wanted to use that. Thank you. So I should use 5 and 9 and hypothetical syllogism. And then 11, I'm going to now combine it with 4 to get there exists x1, R of x1. And that is modus ponens. Now, if you want to start with this one, it's totally fine. Just make sure that you are realizing that every time you use it there exists, you're actually talking about the one that makes line 4 true. So there's another faster way to do this proof if you do that. Questions on this one? So this is just like your old proofs. You'll lose approximately 4 points if you don't use predicate calculus. So if you just put like Q implies R and stuff like that, and there's no X's and there are no for alls, you'll lose about 1/3 of the points. You may choose to do that. I know you're all optimizing your own grade. You have to decide which grade you want to get and how much work you're going to do for it. I used to think, everybody should do everything, but then I realized that, you're human and you have other stuff to do. Amazing. All right, next problem. Prove that square root of 5 is irrational by contradiction. So by contradiction means we start with the negation of the conclusion. So the opposite of square root of 5 is irrational is that square root of 5 is rational. And if your question is, can I write my proof like that? The answer is yes. Whatever abbreviations I use, you're allowed to use on your test. The definition of rational tells me that I can write square root of 5 as P over Q, where P and Q are integers and they're relatively prime. And what does relatively prime mean? They have no common factors. So now, at this point, we know that what we would really like to do is show that P and Q have common factors, because it's the only thing that I could get the opposite of in this proof. So that's what I'm going to try to do. So I'm going to square both sides and cross multiply to get 5Q equals P. That's from math. You're not allowed to write that on proof stuff for logic, but you're allowed to write it for this. It's just regular math, yes? Yes, thank you so much. Okay, so now this means that 5 divides P squared, right? Because the definition of divisibility is that if I can write something as having it factored out times an integer, then it's divisible by that. So this means 5 divides P squared. That's from the definition of divisibility. And we've done this proof in class. I think that I have possibly, I don't have a question. So we'll have to prove this to the side. We'll do it later. So we're going to prove that to the side. So if 5 divides p squared, 5 has to divide p. What kind of numbers make this implication true? So besides 5, what kind of numbers could I put in there? So if something divides a square, how does it divide the root of the square? Always. Like, what numbers can I always put in there? No, not all positive integers work. How about 4? If 4 divides p squared, does 4 divide p? 4 does not necessarily divide p. Let's say p is 2. 4 divides p squared, right? But 4 does not divide 2. 4 is a perfect square. So you obviously can't put squared numbers in there. What other kinds of numbers could you put in there? Prime numbers. Prime numbers will always work. So if someone says, prove that the square root of 16 is irrational, you should say no. It will not work. This is where it breaks. Okay? The entire proof, you could do it with robot brain, but this lemma will not work if you're taking the square root of something that is a square. Okay, I'm glad you don't look shocked. Lemma means a little thing I'm going to go prove on the side later. That's what lemma means, little proof. This is our big proof. Lemma is our little proof. It's not my creation. That is a math word. So if you ever see a lemma in a book, you're like, what the heck is a lemma? I always thought that when I was, an undergrad. It's like, what's a lemma? What's a theorem? What's a conjecture? Conjecture is something we haven't proved yet. A theorem is the thing we have proved, and a lemma is a little thing I proved because I was trying to prove something bigger. Okay, so now I can use modus ponens with 4 and 5 to get the 5 divides p. If 5 divides p, then p is equal to 5 times some integer. That's a definition of divisibility. Now, I'm going to plug this back in to my equation on line 3 and get that 5q squared equals 25k squared. So I have to square p to get that. So that was substitution with line 7 and 3. So now I get q squared equals 5 times k squared just by dividing out a 5. But now I have an equation that looks a heck of a lot like equation 3, so therefore I can also, just from this, can figure out that 5 divides q, right? Because the same lemma that works for p will work for q because p and q are just variables. Well, I forgot to write 5 divides q squared. So I'm going to combine line and 10 together with modus ponens at 5 divides q. But now I have that 5 divides p and 5 divides q by conjunction. And that's a contradiction because p and q were not supposed to have common factors. Okay, I'm not going to do it, but I'm going to show you the structure of the lemma. Doesn't matter if you use Q or P. No. Once you do it with one variable, it works for all the variables. So the question was, do I have to do it separately for P and Q? No. If I prove it for one, it works for all variables. Okay, so you know that 5 divides Q in the first row, and it doesn't in all the rest of them, right? Because a sum is divisible by a number if all the terms in the sum are divisible, but the last one's not. So if every term in the sum, except for one, is divisible by 5, then the sum is not divisible by 5. So all of these are not divisible by 5 by definition, right? I was actually separating the numbers by what their remainder is if I divide by 5. So 5k is all the numbers that are divisible by 5, and all the other ones are all the numbers that are not divisible by 5. So then what I do in order to figure out 5 divides q squared is I actually have to put q squared on here. And I actually have to use q to figure out what it is. So the first one is 25k squared. The rest of them, you multiply out this number times itself and show that all the terms are divisible by 5 except for the last one. So I'm not going to finish that because we have 5 minutes left. That's an easy one. And you also have it on your last homework. So homework 5 had a table that was exactly like that for 3, right? So you can look that up. Okay, so next problem says, prove that for all n in the natural numbers, n cubed plus 2n squared minus n minus 1 is not divisible by 3. So again, to do an arithmetic proof, I want to do divisibility by 3, I need to make 3 rows in the table, 3k, 3k plus 1, and 3k plus 2. And then I'm going to put that in and sub that in. This is a test, so I don't actually want to cube anything because cubing stuff introduces errors, right? So what I'd like to do is factor this into some kind of stuff so I don't have to do so much work. In the first case, this is easy because I can just write 3k in there. And all these terms have 3's in them, and that one doesn't. So 3 does not divide n is true. In the next case, I'm going to, let's say, write n cubed plus 2n squared minus n minus 1 is equal to n squared times n plus 2 minus n plus 1. Let's just write it that way. So if I plug in 3k plus 1 to this, I get something divisible by 3, right? So I don't need to figure out what n squared is in the second row. So this is going to be n squared times 3k plus 3 minus 3k plus 2. So this is divisible by 3, that's divisible by 3, that's not. So 3 doesn't divide n. And in the last one, this is going to be divisible by 3. So I'd like to have a plus 1 in here. So what I could do is put maybe something else. We can just do it. So this will be 3k plus 2 cubed. Now let's do this. Squared times 3k plus 4 minus 3k plus 3. That's divisible by 3. So now I need to deal with this stuff. So I'm going to just distribute this. This is going to be 3k times 3k plus 2 plus 4, quantity squared, 4 times 3k plus 2, quantity squared, minus some stuff that's divisible by 3. This is clearly divisible by 3, right? That's divisible by 3. And then this, I'm going to have to multiply that out. So I did save myself some work. So that's going to be 4 times 9k squared plus 12k plus 4. And this is divisible by 3, that is, and that's not. I have exactly one x, so now 3 does not divide n. You can ignore this next problem. I will not give you one like that. Problem 7, uses the cheat method. So we did plenty of those today. Not going to work that. Problem 8 asks you to use the linear homogeneous formula to find the closed form and prove it true by induction. I will not actually ask you to find the closed form and prove it true by induction. I'll ask you to find the closed form for a linear homogeneous recursion, and then I will separately give you another problem where I actually give you the closed form and have you prove it true by induction so that you don't get messed up by deriving the wrong closed form. Problem 5 asks you to prove this by induction. This problem involves a trick, and you should feel really awesome if you could do this problem, but I won't give you this hard of one on the test. The reason why this one's so hard is because this practice test was made out of a take-home exam that people had more time. So if you can do this problem, you can do whatever I give you. But I'm not going to give you one that's hard. And the last one, we did lots of these last time where we practiced writing summations in terms of prior ones. And that's the whole test. We'll see you on Tuesday.